Hello and welcome back, team, to another APES screencast. In this screencast, we're going to finish Chapter 14, covering sections 14.3, 14.4, and 14.5. In 14.3, we're going to talk about the environmental effects of using non-renewable minerals. Mineral use creates environmental impacts. We can see this with metals and the products they are used to create. We call this the metal product life cycle, and includes everything between the moment that the metals are extracted from the ground and the moment that the product is disposed of. It also includes the processing and manufacturing that happen in the middle. Every step of the product life cycle has environmental impacts. Oftentimes, the impact is determined by the ore's grade. Remember that grade refers to the percentage of metal content in the ore. The diagram at the bottom shows the product life cycle of a car. Removing mineral deposits has harmful environmental effects. There are different ways in which we can remove minerals from the earth, and each way has its own environmental impact. The first type is called surface mining, in which we remove minerals from shallow deposits. In surface mining, overburden has to be removed first. Overburden is the material on top of your mineral of interest. After that overburden is removed, it's considered spoil or waste material. Specific types of surface mining include open pit mining, strip mining, and mountaintop removal. This diagram shows a surface mine for coal. You can see the overburden on top of the coal and how the overburden has to be removed and becomes spoil on the left side. This is the Bingham Canyon Mine in Utah. It's one of the world's largest copper mines and is about 3 miles across. Mountaintop removal in the Appalachian Mountains can be seen on the left here, and strip mining can be seen on the right. Here is another example of mountaintop removal. Remember that mountaintop removal is a type of surface mining used to remove shallow mineral deposits. If you take your mining underground, we call this subsurface mining. Subsurface mining aims to extract minerals from deep deposits. Specific examples of subsurface mining include drift mining, shaft mining, and slope mining. This diagram shows the different types of subsurface mining. There's drift mining, where you dig horizontally underground, slope mining, where you dig at an angle underground, and shaft mining, where you dig straight underground. Let's talk about the potential problems of mining next. The first is subsidence, or the land sinking. We talked about subsidence before, when groundwater is removed excessively. In mining, subsidence can occur when underground mines collapse. Second, there's acid mine drainage. In acid mine drainage, iron sulfide in the earth reacts with oxygen and water to produce sulfuric acid. This sulfuric acid can then escape the mine, affecting the environment around it and killing organisms. And finally, there are health effects, like black lung disease in coal miners. A diagram, a photo, and the chemical reaction for acid mine drainage are shown here. Remember that iron sulfide reacts with oxygen and water to produce sulfuric acid, which can then escape the mine and affect the environment. These photos show how black lung disease progresses in coal miners over time. In black lung disease, coal dust gets lodged in the lungs, where it forms nodules and scarring. Over time, it impairs the ability of the lungs to function. The environmental effects of mining can be seen in the world's gold mines. At about 90% of the world's gold mines, cyanide salts are used to remove gold from gold ore. Unfortunately, cyanide is highly toxic and potentially deadly. Instead of cleaning up these mines, which we call environmental remediation, mining companies instead declare bankruptcy to avoid it. Just for your reference, a diagram of how cyanide is used to remove gold from ore is shown at the top. On the bottom is a photo of a gold mine that uses cyanide. After you remove ore from the earth, you have to process it and remove the impurities that are in it. Once the impurities are removed, they're called tailings. Two photos of two mines and the tailings that they've produced are shown below. When you heat metal ore to remove the metal in it, we call that smelting. Smelting creates air pollution, specifically sulfur dioxide and particulates. Also, water has to be used for cooling. The wastewater that smelting produces is toxic. In section 14.4, we're going to talk about how we can use mineral resources more sustainably. One way we can extend the life of metal resources is by using substitutes like silicon. The development of new materials to replace metals in some instances has been called the materials revolution. We can research and invest in new technologies. Things like nanotechnology, ceramics, and high-strength plastics have the power to replace materials that are limited in availability. Unfortunately, substitution doesn't always work. One example is platinum. Platinum is an industrial catalyst that we do not have a substitute for yet. Recycling and reusing are more sustainable than mining. Recycling and reusing have a lower environmental impact than mining and processing metals from ore. The periodic table on the lower right shows what elements can be recycled and the actual rates of recycling that happen. This table lists different solutions we can use to more sustainably use non-renewable minerals. In section 14.5, we're going to talk about some of the Earth's major geologic hazards. We first need to understand that the Earth's crust is broken up into pieces called tectonic plates. These tectonic plates float or drift on the semi-solid, partially melted asthenosphere. Much of the world's geological activity takes place at these plate boundaries. The map on the bottom shows the world's major tectonic plates and plate boundaries. Plate boundaries are where two plates meet, and there are three different types of plate boundaries. The first is a divergent boundary where plates are spreading apart. At a divergent plate boundary, you'll find seafloor spreading, rift valleys, volcanoes, and earthquakes. One example of a divergent plate boundary is the Mid-Atlantic Ridge that runs down the middle of the Atlantic Ocean and through Iceland. Divergent plate boundaries are where new crust is made, and that's why you'll find an oceanic ridge and seafloor spreading in an underwater divergent plate boundary. Convergent plate boundaries are where two plates meet. At a convergent plate boundary, you'll find trenches, mountains, island arcs, volcanoes, and earthquakes. Two examples of convergent plate boundaries are the Mariana Trench and the Himalayan Mountains. At the Mariana Trench, you have one plate going underneath another, creating the trench. In the Himalayas, you have two plates that meet and thrust upwards, creating the mountains. The Aleutian Islands that separate the Bering Sea from the Pacific Ocean are an example of an island arc created by a convergent plate boundary. This diagram shows how a convergent plate boundary can create volcanoes. One plate going underneath another causes melting. This creates magma, which then rises and forms a volcano. The third type of plate boundary is a transform boundary. These occur where two plates slide past one another and are often the site of earthquakes. One good example is the San Andreas Fault in California that separates the Pacific Plate from the North American Plate. Every time there's a sudden shift in these plates, we have earthquakes. This table summarizes the similarities and differences between the three different types of plate boundaries. This map shows the major plate boundaries and highlights a transform boundary in North America where the San Andreas Fault is, a convergent boundary in South America, where the Andes Mountains are, and a divergent boundary in the Atlantic Ocean, where the Mid-Atlantic Ridge is. When magma rises through the Earth's lithosphere and reaches the Earth's surface, we call this a volcano. A volcano erupts when there's a sudden release of lava, hot ash, and gases. This is a diagram of a volcano and an eruption. It also shows how when a tectonic plate shifts above a hot spot, it can create new volcanoes and leave behind extinct volcanoes. This is how the Hawaiian Islands formed. This is another photo of a volcanic eruption. It also shows how when magma reaches the Earth's surface, it then is called lava. Places along a plate boundary where earthquakes occur are called faults. An earthquake occurs when there is breaking and shifting of rock at a fault. When an earthquake occurs, energy is released as vibrations in the Earth's crust called seismic waves. An earthquake begins or originates at the focus. The focus is normally underground with the epicenter directly above it. An earthquake's magnitude is how severe it is, and an earthquake's amplitude is how big the seismic waves are. The Richter scale was created to express earthquake magnitude based on the readings of a device called a seismograph. The Richter scale is logarithmic or based on powers of 10. For example, a 7.0 earthquake is 1,000 times stronger than a 4.0 earthquake. The largest ever recorded earthquake was a 9.5 earthquake that occurred in Chile in 1960. The Richter scale can be seen on the left here and the potential damage of different earthquakes at different magnitudes. The aftermath of the Chilean earthquake of 1960 can be seen on the right. This is another depiction of the Richter scale, showing some of the major earthquakes that have happened in the past and their magnitudes. In this diagram, you can find the focus, which is where an earthquake originates, the epicenter, which is the point on the Earth's surface above the focus, seismic waves, and some of the effects of an earthquake. This is a photo showing the aftermath of an earthquake in Haiti. Underwater earthquakes can cause the ocean floor to suddenly rise and drop. This can create a series of huge waves called tsunamis. Tsunamis can travel several hundred miles per hour at sea. As they approach shorelines, they'll slow down, but they'll increase in height. An example happened in December of 2004 in the Indian Ocean. A tsunami there was caused by a 9.15 magnitude earthquake that created 31-meter waves. The aftermath of tsunami can be seen in the photo here in Japan, where a tsunami brought a boat in and caused many deaths, including the one being mourned. These two aerial photos show what happened before and after a tsunami in Indonesia. In 2011, there was a very significant tsunami that occurred in Japan. This tsunami caused almost 16,000 deaths and caused damage to nuclear reactors that led to leaking radiation. These are before and after photos of a nuclear reactor in Fukushima, Japan. After the nuclear reactor was damaged by the tsunami, it leaked radiation. This diagram summarizes how underwater earthquakes cause tsunamis and how tsunamis will slow down but increase in height as they approach coastlines. In this close-up, you can see how an earthquake creates the initial waves of a tsunami event. People around the world are trying to find ways to mitigate or lessen tsunami damage. One example are buoys that have been set up by different countries to detect tsunamis early. A buoy is shown here on the left, and the location of different buoys set up for early detection is shown on the right. People are also trying to preserve and restore mangrove forest and coral reefs so that they can absorb wave energy and prevent coastal damage. This is a photograph of a mangrove forest. Mangrove forests can absorb tsunami wave energy and prevent coastal destruction.